entropy, especially in the context of ADS or CFT correspondence, has made a lasting impact on theoretical physics. A fellow of all three national science academies, recipient of the Shanti Sharup Bhatnagar Prize, and long-standing editor of the Journal of High Energy Physics, Professor Mukhi also brings a rare confluence of science, music, and public outreach. We are honored to welcome Professor Sunil Mukhi to share his expertise with us. Sir, the platform is all yours.
Thank you so much. I hope you can hear me well.
Yes.
So in order to share my so-called expertise, I first have to share my screen. And so I hope you'll support me when I give a little prayer to the God of screen sharing that this should work. Usually it doesn't. So let's see what it says. Present to everyone. Very good. Start broadcast. Very good. Did anything happen? Something is happening there. Here. Well, the God has not been very kind. I'm logged in on two devices, and I was hoping to write on this. You should be able to see my notepad. I'm really not sure what to do next, and I don't have a PowerPoint, so there's no way I can send it to anyone. Yes.
Notepad is not seen?
Sorry?
I mean, your notepad is not being visible or what?
Well, I can't see it on the... Can you see it?
No, it is blank as of now.
There's some brown background and blank, right?
Yeah.
So that is the second me. That is the one which should be showing the notepad. And so let me try again and see what options I have.
Just disconnect. So
let me stop sharing. Let me stop sharing first. Then let me again say share screen. Screen broadcast stopped. Now let me say share screen. Present to everyone. Screen broadcast. Google Meet. Start broadcast. 2, 1, 0. So now it is actually broadcasting and should be, and then I can go to my notepad, but no, nothing is coming on your screen and it's really annoying. Let me try to see if is there something that organizers have to do? This is not clear to me.
I don't think you have to do anything.
This is really annoying.
Just a minute, wait, we'll sort it out. It's a notepad.
Okay, I have one idea. Give me 1 second, please.
Yeah.
Maybe this is what I need. Oh, I cannot use camera well. Good. So that's good.
Put off your camera.
Yeah, it is off. It has been off. Camera and audio are both off from the tab. And it's simply...
No, from your side also, where you are in Gmeet, you just put it off.
Yeah, it is off already.
No, I can see you, right? So you.
Oh, that. You want me to put that camera off? Okay.
Yeah.
Now that camera is off. That didn't help anything.
No.
Unfortunately, Gmeet is really a bit more complicated than Zoom.
It seems.
Yeah, I'm afraid so. Okay, let me quickly try to... in the middle of everything, by the way, there's also no power here. That's, of course, a different matter. But I have some backup power, so I am hopefully okay. iPad screen sharing, Google Meet, not visible. Sharing your screen may be disabled due to admin settings or meeting host controls.
So, Muksud, are you there? Can you please see to it? Is anything disabled there?
Yeah, that is important.
Share their screen, it's allowed. Share chat messages, send reactions, turn on their microphone, everything is...
Because I tried...
let contributors should be on.
Settings. Yeah, nothing in the settings. Yeah, I was quite confident that this will work. Again, I'll stop sharing and see what happens. Okay, stop sharing. Start sharing.
Your tab screen is already shared with your, iPad screen is already shared in your machine, right?
Yeah, that's what I just stopped it and I'm starting again. Now it is saying screen broadcast. Everything on your screen will be recorded. Google
Yeah.
Meet start broadcast. So I'm clicking on start. It says 3, 2, 1. And now it shows that this broadcast is going on. Unfortunately, at your end, what you are seeing is only the brown screen and nothing more.
Yeah.
That is the strange problem. Uh, okay, one thing I can try to do, I'll log out from my laptop
Yes, and we open from tab only.
and see if that helps. So I'm leaving from laptop now. Hello, can you hear me
Yes.
still?
Yeah, yeah.
Hello, can you hear me?
Yes.
Hello, are you able to hear me now?
Yes.
Hello,
Yes.
you can hear me, right?
Yes.
Okay, so good. So far so good. So now let's try screen sharing. Same story.
Mm,
Now it's sharing, supposed to be.
that is good.
And it should be showing this notebook. Are you seeing it?
No.
No.
No. This is very
Okay.
strange. It should not be the thing.
Sorry?
No, this is very strange. It should not be the thing.
I know. I will again log out and log in from this iPad. Let me just try that. Okay, I'm back. Can you hear me and see me?
I can hear you.
Okay. You should also see my face at a weird angle. So now let's try to share the screen. Okay, supposed to be sharing. It's somehow buffering. I don't know if it is really doing the job. It is going around. Something is going round and round.
Yeah. The whole screen is seen.
Oh, very good. And now you can see this?
Yes.
Beautiful. Okay,
Yes.
I can start. You'll have to do
Please start.
without seeing
Please,
my...
please go ahead.
Yeah, you'll have to do without seeing my face. I'm sure that's a plus point. But anyway, good. So let me start, and I really apologize. Okay, so the talk I've planned to be on quantum mechanics, relativistic quantum theory, and quantum fields. And let me first start by saying what I'm trying to communicate. I'm not communicating anything very modern. Unlike Sandeep, I will not be telling you about recent advances in entanglement and so on. Instead, I want to kind of sketch a pathway, which is QM to relativistic QM to QFT. And I have two reasons for doing this. First of all, you will already get a lot more technical talks in the next 4 or 5 days. So you're going to hear about modern things related to quantum technology and entanglement. But in order to appreciate those things, we really need to feel the meaning of quantum mechanics and why it is there. And I personally am very keen on the question why. And I sometimes I feel disappointed in textbooks which start by saying In order to learn quantum mechanics, there are 6 axioms. There is wave function, there are operators, there is state, there is superposition, there is expectation value, there's eigenvalue. That is not how anything developed. That is how we see it now. So it will be nice to see sort of what were the key steps in developing it, because I think it will make us understand the structure a little bit better. So I'm going to try and do that. Also, although quantum mechanics in its original non-relativistic form is often taught is always taught in undergraduate level in physics, there's less of an emphasis on relativistic quantum mechanics. I actually find even many practicing research physicists are not so comfortable with it, and even less of emphasis on quantum field theory, except in certain communities of people who work in high energy physics and gravity. So, but I think that QFT, quantum field theory, that is the ultimate formulation without which we really don't know what is quantum theory. So I really want to motivate that. Okay, so let's start. In between, I will stop for questions because I feel better to get feedback. So whenever I stop for, please keep your question in your mind ready. As soon as I stop for a question, please do ask. I'll be happy if questions are asked. It really helps me to grasp that how the audience is perceiving this. Okay, so one of the interesting experiments which made it clear that that classical physics cannot be completely right was an experiment which we don't even need to perform. It's called stability of hydrogen atom. So what is this experiment? Well, it's nothing. It is just the fact that we exist. The fact that we exist and we are made out of many atoms, including, many atoms, and that, from day to day we don't disappear. That is an evidence that the atoms are stable. Hydrogen I picked only because it's simple. All atoms are, in the sense I'm describing, stable. Some atoms, some elements may be unstable, but the stability problem I'm going to mention would have caused atoms to decay on a time scale of something like 10 to the minus 11 seconds. That's not at all what we mean when we talk about elements being unstable. So it's certainly true that things don't decay on a time scale of 10 to the minus 11 seconds. Where do we get this time scale? I'll just explain it in a minute. So as you know, accelerate. So hydrogen is modeled by a proton and an electron, and the electron goes down the proton. And that's a sort of classical picture, like the moon going around the Earth. But so in this process, the electron, this one, is constantly accelerated. I hope my writing is visible. I can't make it better than it is, but electron is constantly accelerated, and it's accelerated perpendicular to itself. That is always how central force motion works. Something is pulling it. It is the Coulomb force, so it's constantly accelerated. And accelerated electron gives off what is called synchrotron radiation. That's a more modern word, but there's an older way of thinking about it. It's just Larmor formula. It's the same thing. And it says that if E is the energy of that electron, then as a function of time, it will change in a negative way. That means the energy will keep decreasing. And the formula is that is this, where Q is the electric charge in some units, then A is the acceleration, and C is the speed of light. So this is a formula which one can derive. It's a little bit advanced side of electromagnetism, but it's a lovely formula, and I would say that because of its impact in accelerators physics, and also because of its use, which I'm discussing now, It's a very good formula also for you to consider teaching if the students are able to follow the derivation. Now, with this formula, you can actually derive so energy of the electron orbiting the proton is constantly decreasing. Okay, so you can use it to derive the rate of fall. So the picture is that if something has decreasing energy, then obviously it will go into smaller and tighter orbits like this until it falls into the center. And then the atom is not there anymore. And you can easily calculate that, and you find that R as a function of time goes, it's a very interesting formula. It goes like the initial radius cubed minus 3 times kt, all this to the power 1/3. This is the initial radius. T is the time. What is k? It's a constant, and we can calculate the constant. And k comes from so k is, turns out from using Larmor formula, it's something like 3 times 10 to the minus 21 meter cubed per second. Okay, and with this, you find that the time taken for the electron to bang into the proton is 1.6 roughly into 10 to the minus 11 seconds. And so you see the beauty of this experiment. There's no experiment. If everything collapsed in 10 to the minus 11 seconds, then there would be no Earth, no life, no planets, no stars, nothing, literally nothing. There couldn't be any atoms. They just would all disappear. If they tried to form, they would disappear. So this can't be right. Okay, so it's a contradiction. And it's a very sharp experimental contradiction. There's no simple way. You can ask, maybe this formula is approximate, maybe we need relativity, maybe we need something else. You can try to add all the things that we know, which are the forces acting on this electron, and you will just always find that it falls in very, very fast. Okay. So the question is something new needed. And I always like to suggest that this slogan, something new needed, should be communicated in a course on quantum mechanics, especially to beginning students, because they come at a time when the subject is seen as sort of finished or already established. And I really would like them to realize that it was not just dictated by somebody. So I tell students, you see history of quantum mechanics as dictated by old German men with beards and wearing suits. But it was not that because they were old or powerful or men that they dictated the laws. They were forced to make some laws just to explain what they were seeing. So that is how science develops, especially physics. Good. So that's one example, this hydrogen stability of the atom. Let's call this example 1. Example 2, I don't have to dwell on in detail. It's the famous double slit experiment. Sandeep spent a nice amount of time on it. And the amazing thing is that, I'll just repeat, is that even if I fire particles,
মানে ভিটামিন ডি3 থাকতো, ক্যালসিয়াম থাকতো, ডায়েট হইতে তো হতাম।
Yeah, you need to mute your microphone, please.
তাই তো ক্যালসিয়াম কার্বনেট একটা দিছইন, প্রিগাবালিন একটা দিছইন।
Organizers, I don't know what's going on. Okay. So here are the two slits, and here I'm firing particles, which are little dots.
Sorry, Shubhaguru, what did you say? I didn't follow.
Who? Sorry, are you asking someone else?
Yes, Sunil, what happened actually? You were asking the organizers?
Yeah, because I could hear somebody's voice.
Okay, I understand.
Ah.
I understand. Yeah, okay, fine.
Yeah, okay. So these particles actually can be even bullets, and in principle the same strange effect happens, but bullets are so big that the effect is practically invisible. But if the particles are electrons, then in fact they make this peculiar interference pattern on the screen behind, which means somehow one electron can cancel another electron. For example, in this place or this place where the waveform is minimum, it means that one electron and another electron have cancelled, which never can happen in normal life in classical physics. So this suggests two things. First of all, again, need something new needed, this slogan, which we should always appreciate. But also, it suggests a wave-like nature for particles. I will advise also, if you go to YouTube, you will see a beautiful video, a few different videos. One was made by Hitachi Corporation, where they actually fired electrons at a double slit. Of course, it's not a double slit. It's something where the electron can only pass through two things, like here, and the rest is blocked by some means where electrons cannot pass. And even though you fire the electrons one by one, after a certain amount of time, this pattern that I've sketched here builds up, which is crazy. This is what Sandeep, when he said that, if you're not shocked by quantum mechanics, you should be. I mean, it's completely crazy that I'm firing one particle at a time, and the next particle is erasing what the previous particle did and building up this kind of interference pattern. After a sufficiently long time, which might be 12 hours or 24 hours. It's completely crazy. Actually, I still find it crazy. But you can watch the video so that you know it's true. And here the key idea was the wave-like nature. Okay. The third one, which is much talked about, is the photoelectric effect. Here I won't go into any details of the effect, but clearly there was a formula for black body radiation, and that formula simply doesn't go down at high energies as it should. And this suggesting that a black body radiates infinite total energy, which is not possible. So again, something new was needed. And here Planck gave the suggestion that light comes in particles of energy E equals h nu, where nu is the frequency of the light. Sorry, I keep saying photoelectric effect when I'm talking about black body spectrum. Somebody should have stopped me. Is also the photoelectric effect, in the sense that gives the same confusion, but I meant here talking about black body spectrum, I'm sorry. So in this radiation that a black body gives off, if nu is the frequency, Planck proposed that the energy, that there are particles being given off, and the energy of each particle is proportional to frequency. Now, this was motivated by many things, and again, photoelectric effect strongly justifies this. So let's combine. Actually, we have both experiments. And says that the energy of each particle is proportional to the frequency of the corresponding wave. You see, frequency is not a property of a particle, okay? And energy is not a property of some part of a wave. So here, instead, he ascribed energy of a particle to frequency of a wave. This was a new idea, a very, very new idea. And for this, he had to propose a proportionality constant, because this and this don't have the same dimension. So simply there has to be a constant, and it's known as Planck's constant, h. Okay. So this much was for light. Now I want to emphasize that the fourth step, for me it's the most beautiful, is de Broglie, who said, okay, before we get to de Broglie, let me just backtrack for 1 second and derive one small consequence of E equals h nu. If you think for light, we have certain formulae which are true only for light, and I can use those formulae here. So first of all, the energy of light, let me just get down my expressions so that I don't write anything wrong. Yeah, good. So the energy of a particle traveling at the speed of light, as per relativity, just energy of a classical particle, if we just take the limit when it goes near the speed of light, then the relation Einstein gave us was that the energy is speed of light times the magnitude of the momentum. And otherwise, as you know, in relativity, the relation is E equals square root of P squared C squared plus M squared C fourth. And of course, if M goes to 0, which is the case for photons, then this relation just goes to that relation. Okay. So if we do this, then we find that P magnitude is equal to H nu upon C. All right. But can we find a relation between P and something which is wave-like? So remember, in all of these equations, the left side is a particle property like linear momentum or energy, while the right side is a wave-like property. Okay. And the way we see this is to realize that nu in a wave, frequency of a wave, is related to something called the wave number. Okay, and it is basically 1 by mod k, or maybe it's 2 pi by mod k. Somebody remind me. 2 pi by mod k, I think. Keep forgetting these numbers. Yeah, the frequency rather, excuse me, I got it wrong, that's the wavelength. The frequency is C times K upon 2 pi. Okay, so K is a wave number, is a wave vector actually. And you see, K carries more information than the frequency. Numerically, it's equal to the frequency up to some constant factors, but it also has a direction. And you can see that because P magnitude is proportional to nu, and nu is proportional to mod of K, we can guess a relation between P and K directly, and we find that P is equal, first of all, we insert this second one, this one, into this one, and C cancels, and we get H by 2 pi K. All right, we are still talking about light only. And now this H by 2 pi, we give it a new name. We call it H bar. So this is H bar. Sorry, this relation of this H bar mod K. And now we can make a little bit of a leap. If the magnitude of momentum is proportional to magnitude of the wave vector K, and both are vectors, then it should be the case that the momentum is also proportional to the vector itself. Of course, this is not a mathematical implication, but it's a very good physical guess. Why? Because what does K contain other than the magnitude? It contains a direction. What is P other than its magnitude? It's a direction. And what is the direction in case of particles? Is the direction that the particle is moving. And what is K in the case of a wave? It's the direction in which the wave is moving. So obviously they should be equated. So physically reasonable. And you'll see here that quantum mechanics proceeded by a series of physically reasonable steps and assumptions. After writing them, people would check them carefully to see if they make sense. It's good to be creative. It's also good to be a little critical and check again whether the things which you are claiming are making sense. And now came a huge step. Okay, and this is all again for light, only for light. We simply got this relation from Planck's relation. It is actually Planck's relation in some other, in terms of some other variables. And then we removed the magnitude sign and said it's a vector relation. Planck is a scalar relation. E equals h nu. This is a vector relation, so better. Maybe we get more information. But now de Broglie comes along and he's writing his PhD thesis, and he says maybe P equals h bar k for all objects, not just light. And that's why this relation is called the de Broglie relation. But I need to tell you what is the motivation to think such a thing. Okay. Up to now, if you see, if I can go up, this formula is Planck's. This formula comes from photons traveling at the speed of light. Then this is true again because of that. Okay. So everything follows for objects traveling at the speed of light. And as we know, only light itself travels at the speed of light. When we start saying that the relation is true for matter, we are saying something a little different. So let's again step back. What does this relation say for light? It says we have a wave. Everybody knows light is a wave. It has a wave vector. Okay. It is saying actually this wave describes also a particle, and that particle has this momentum. So the implication is this way. If I give you a beam of light, you will know the wave vector because you know the frequency, the wavelength of that light. And from that, you can calculate this and assign this momentum to your light. It's very unusual to assign momentum to a piece of light because before quantum physics, light was not made of pieces at all. It is only after quantum physics that light is proposed to be made of photons, and this is the momentum of each photon. Now for matter, let's say slowly moving matter like electrons, it could also be fast moving, but these are particles which are not always moving at the speed of light. We know their momentum. Given an electron, you can measure its momentum. Just like given a bullet or a rock or a stone or a car, you can measure its momentum. And the new thing is to say, but actually this particle is a wave and the wave has a wave number k. So the implication in this case is this way. So the same formula, this one and this one, but in light it's telling us the momentum if we know k, and in matter it's telling us k if we know the momentum. When I say if we know, I mean these are the classically observable quantities. I hope this point is clear. So there's a small calculation which I'll quickly go through, which de Broglie actually did to motivate his claim that this relation is true for everything. And here we'll do the following. Let's notice that in non-relativistic physics, I can think of the energy of a free particle as p squared by 2m. And from this, I get the relation that del E by del P is equal to P by m, just by differentiating. But as you know, P is mv, so this is the velocity. So the velocity is the rate of variation of the energy with respect to the momentum. Now this formula is actually true also in relativistic physics. It's a nice exercise. I invite you to think of doing it. I think I was asked to propose some problems or puzzles. This is the one which you can check. What do you have to do? In relativity, this gets replaced by square root of p squared c squared plus m squared c fourth. And p gets replaced by this. P gets replaced by mv upon square root of 1 minus v squared by c squared. So from these two facts, you can perform the differentiation of E with P, and you will again find that the answer is V. So del E by del P is V. Good. Now, what are these properties of? They are properties of a relativistic particle, relativistic or non-relativistic. Most general kind of free particle obeys this relation. Okay. Now let's think of properties of a wave. So this is for a particle. For a wave, classical wave, and remember that by the time of 1 century ago, people had been studying classical waves for centuries. I mean, Newton, people before that also, water waves and sound waves and all that, very well studied. And one concept that was developed in those studies was the group velocity of a general wave, which I'll call Vg. And this is defined as the rate of change of the frequency with respect to the inverse of the wavelength. Okay, this is true for general waves, including sound waves. If I differentiate, because in general, nu is not just 1 by lambda or c by lambda, that's only true for light. And obviously, then Vg will come out to be c. But in a general wave, we have what is called a dispersion relation. So nu is some function of lambda, maybe a very complicated one for these elastic waves like sound and water and so on. But if I do this differentiation, I get Vg. Okay. So now the de Broglie's guess is to equate this particle property and this wave property. So I'm going to box this and write wave. And now I want to equate them. So I find that dE by dt should be equal to d nu by d 1 by lambda. And now in this relation, if I use E equals h nu, I immediately find that P is actually equal to h bar k, which is the same as h by lambda. Now here, these are magnitudes, because lambda is just a number, lambda is not a vector. So magnitude of k is the same as inverse of lambda. And of course, then again, I'll make the guess. So there are two guesses. One is that group velocity of a wave is same as the velocity of the corresponding particle. So matter is also a wave with a group velocity equal to velocity of the particle. And then the guess is that this above relation is really a vector relation, P equals h bar k. And now something really remarkable happens. Waves are very well known and I'll explain this a little bit, to have an uncertainty relation between x and k. This is old wave theory. It has nothing to do with quantum physics. Okay, and what is the idea of this uncertainty relation? Well, supposing I have, so k, remember, is a magnitude and a direction, and it tells me the frequency. Okay, is the basically proportional to the frequency. If I have a monochromatic wave like this, fixed k, then of course x is anything. Okay, there's no point on this monochromatic wave where you can say here is the wave. There is no crest. There are, or if you like, there are all the crests, but there's no place where you can say most of the wave energy is concentrated. This wave, which is we call plane wave, is just distributed all over space. Okay, so x is completely uncertain. On the other hand, supposing my wave looks like this, okay, it's a superposition of many k's. I need to do that in order to get a wave which looks like this. And now I can say that this is roughly x, that the peak of the wave, most of the energy of the wave is localized in this region. So we have something like roughly fixed x. It's always roughly. But k is uncertain because this wave is not made up of a single frequency or a single wave number contribution. If it was, it would look like this wave. It's a very different looking wave where the where most of the wave intensity is concentrated in a small region, and we can only get that by superposing a lot of wave numbers. Okay. And in fact, now you can use the mathematics of Fourier transform, which relates these two, to conclude that if delta x is the uncertainty in x and delta k is the uncertainty in k, then for any wave, which could be either of this form or anything in between, you always get a bound that this is greater than or equal to half. This is an uncertainty relation for waves. And I don't know, books mostly don't emphasize this. But it's been known for a long time. This was not made up by Heisenberg. Okay, the fact that waves obey an uncertainty relation is nothing new, even a century ago, but it's a relation between position and wave number. And it's a purely wave-like property, nothing quantum about this property. Okay. But de Broglie's relation magically transforms this. If we assume, and this is the step of quantum mechanics, that P is the same as h bar k. Sometimes I'm using vectors, sometimes I imagine I'm in one dimension. I hope you don't mind. Then the above relation tells me that delta x delta p is greater than or equal to h bar by 2. Where did h bar come from? It came from this relation. From this relation. And it simply converted this uncertainty principle of waves into this uncertainty principle, which is now written in terms of particle-like properties. X and P, position and momentum, are particle-like properties. So this is how I see the way that wave mechanics and uncertainty came. It came by the assumption, very bold and very simple, that particle momentum is proportional to the wave number of a corresponding wave, and this proportionality constant is the same as the one Planck assumed between energy and frequency of light divided by 2 pi. The 2 pi, actually, we already saw why it comes, I think. It comes from this 2 pi here. Well, yeah, it comes from this relation, the fact that nu has a 2 pi in its relation with k. So therefore, from E equals h nu, I go to P equals h bar k. That's the basic idea. Okay, so this is one point I wanted to emphasize. I'm sorry if it was very trivial and you already knew it, but anyway, I'm happy to answer any questions about this. Then I'll move on. Questions, comments, anything? Is anyone there? Can anyone hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
I see. Okay. And there are no questions? Okay. I don't know whether that means this is very
Probably not
boring.
at this stage, but we can go ahead.
Okay. Okay. Atri, tell me
Good
frankly, this is very too
morning.
elementary. I am wasting everyone's time or what?
No, it's not like that. Sometimes it's required. If there is no flow, then I mean,
Okay.
yeah,
Good.
flow is required.
Thank you.
Thank you.
But it is elementary, so I will go on to more complicated things now. Okay. Thank you.
Good.
Okay.
Am I audible?
So what is the next step after this happened? Is to formulate an equation, and you know this equation for the wave. And of course, this required introduction of something called the wave function, which satisfies that equation. And again, wave function is nothing new. Wave function is the function which describes the actual wave in a real sound wave or water wave. It's just that here we are associating this to a particle. That is the shocking and new thing. Okay. And here, then the idea was that energy in non-relativistic physics is p squared by 2m plus v of x, where this is second term is the potential. And now we use again something which is well known in wave mechanics. That is not quantum theory, but old wave, the study of waves. That because of Fourier relation between the position of a point on the wave x and k, the wave number, we have that k is same as minus I d by dx. We can even generalize it to a 3-vector equation that it's minus I gradient in x. There's no h bar in this relation because wave number has inverse dimension, which is inverse length. So this is perfectly consistent. But again, P equals h bar k tells us that in fact this P is equal to minus I H bar gradient X. And so Schrodinger thought, very good, maybe what is supposed to happen is that this energy function is supposed to be a differential operator acting on the wave function, which gives me its time evolution. So minus I H bar d by dt of psi is equal to minus H bar squared by 2m gradient of x squared plus v of x of psi. And psi depends on x and t, and then you solve it and you get now there are many things. This is a coupled partial differential equation because v can depend on all three components of x. You solve it, you have some boundary conditions, you use some Green's function method. See, we do simple problems like step function or harmonic oscillator, but of course you can do very complicated things. You can do them numerically also, and you get the wave function. And in principle, you get sort of complete description of the system. So the wave function becomes the central quantity. Okay. Now, up to now, we made it look like the Schrodinger, so this Schrodinger equation. And this is a very special Schrodinger equation because it's for one particle. Now, nowhere in the world there is such a thing as having only one particle. There are typically millions of particles around, but nothing stops us generalizing this to a wave function which depends on n particles. Okay, so in that case, it minus a I h bar d psi by dt is the same, but it's a function of n positions, and then this is equal to minus summation of the gradient squared for each particle with h bar squared over 2m. Okay. The masses can also be different, so it's a little more complicated. Let me write it better. So you can have particles of different masses mi, and then you can have the gradient for each of them, and then you add v of all the xi. And I'm sure you have seen many examples. For example, V can be a pairwise potential. Supposing they are all charged particles, then it is a pairwise Coulomb potential, and like that. So this is the n-body Schrodinger equation. Now, one thing to emphasize here is that if I want to write the equation, I have to decide how many bodies are in my problem. N could be 1 or it could be a million, but it can't be 1 today and a million tomorrow. It can't change. Okay, fixed. And this is somehow in accordance with what we believed before special relativity, which is that particles are just fixed things. Once there's a particle, there'll always be a particle. It doesn't disappear. It can possibly merge with another particle to give a bigger particle. Those are what we call inelastic collisions. But certainly one particle can't cancel out another particle. And so this n will remain fixed. We'll come in a moment to the discovery which forced us to change that view, that n can be chosen to be fixed. Okay. Now, I said that from Schrodinger equation we can calculate lots of things. It was a wonderful time when people simply got busy calculating the spectrum of the hydrogen atom, then trying to do helium atom, then trying to do molecules, trying to do more and more things. The more complicated it gets, the harder it is to explicitly or analytically solve the equation, but conceptually there is no difference. Okay, an atom which has 20 orbiting electrons, in principle you can write the Schrodinger equation for the nucleus and 20 orbiting electrons, and you can incorporate all the forces between them and write it, and maybe a very good computer will solve the dynamics for you and you'll get some answer. Okay. Now, in the process of doing this, the concept of spin emerged as follows. It was found that somehow, even though the atom has energy levels, let's call them E1, E2, E3. So, of course, you know now, I skipped over that once you solve the Schrodinger equation, you find that an atom with a charged nucleus has discrete energy levels, and now there's no allowed energy in between them. So here there's nothing. There's no particle, no electron can have any energy between those, only here or here or here, like that. And once you accept that, then you realize that Larmor's formula is wrong, because the electron cannot gradually spiral. So somehow the electron, once it is happily sitting in one of these levels, the laws of quantum mechanics says that it will remain there forever unless we hit it. So that is what is called a stationary state. And once we have stationary states, then the problem of instability of hydrogen atom or any atom is solved. And this is a huge problem solved. This is a huge victory for quantum mechanics. Okay. Now, the next stage, though, is that when people started to examine these levels, and they put the atom in a magnetic field, they found that suddenly these are not the levels, but instead the levels split. Again, I want to emphasize this was an experimental fact, Zeeman effect and many other related effects. But all of them tell us that, first of all, it looks like there's not just one electron sitting in this level. Even in the hydrogen atom, there seemed to be a possibility of it sitting here or here. So there are two things that, it seems to have some attribute which is two-valued, which determines whether it is at this level or at this lower level. So that splitting concept was very puzzling. And it was Uhlenbeck, I think, in a famous paper, Uhlenbeck and Gaudsmit, who said that electron itself has an angular momentum h bar over 2. And these two states actually are where the angular momentum is plus and minus h bar by 2. So it depends on the alignment. And these two states arise in a magnetic field. Why? Because the electron, having this angular momentum, starts to behave like a magnetic dipole. And of course, we know that if there's a magnetic field going through a system, then a magnetic dipole in it will rotate and it'll experience a force. And the force of that thing is given, or the energy rather, is given by mu, the dipole moment times the magnetic field. Okay, so now this was already known that an orbiting electron has a dipole, creates a dipole, right? Because if a particle goes in a circle like this and it carries a charge, it's like a circulating current. And the circulating current will create a dipole. It's the same way that a current in a solenoid creates a magnet. Okay, and so this gave a kind of a model for how the electron works. But one should not say that the spin, this h bar by 2, is due to anything circulating. People try to keep guessing that something may be circulating in it, but ultimately we know that nothing is circulating, just the electron is born with that angular momentum. You cannot change the angular momentum, intrinsic angular momentum of any electron. Every electron is identical and has h bar by 2 spin, although you can change the weight points. You can orient it differently, but basically every electron is exactly the same as every other, and you can't speed up its rotation or slow it down. And here, something was already known, which is that, so there was a comparison being made. This was a model, as I said, the model was not exactly right, but it helped us to reach the formulae. Electron orbiting gives a magnetic moment by this model which I've just shown you here. If the electron is orbiting like this, then we get a magnetic moment like this. And as we know from the laws of quantum physics as they were developed, the orbital angular momentum is n h bar, where n can be 1, it can also be 0, 0, 1, 2, 3, dot, dot, dot. This is the allowed amount of orbital angular momentum as per the laws of quantum physics. Now, with this, a unit was found. So, for every angular moment, every orbiting electron, there's a corresponding magnetic moment. But what is the value of that magnetic moment? This led Bohr to propose a unit. Okay, and the unit, let me just make sure that I don't make any mistakes. The unit is E by 2m times the spin s. So this unit is called a Bohr magneton. Okay, you can say EH bar by 2m is the Bohr magneton. It's a unit of magnetic moment, and it would be exactly the magnetic moment of an electron going in an orbit of n equals 1. And if n is more than then the magnetic moment will be just a multiple n of this basic unit. So far, so good. Now, you would guess that because electron has also got spin, then the magnetic moment of the electron should be the unit half h bar times E by 2m, or half a Bohr magneton. Okay. This is what you would naturally guess if the model is correct, that the spin behaves exactly like an orbital angular momentum. But this flatly disagrees with experiment. An experiment found that instead the magnetic moment of the electron is a number g times the Eh bar by 2m, and g is not, sorry, yeah, this, and g is not 1, sorry, times half of this. Yeah. So g is not 1 as you would expect in the orbital angular momentum theory, but it's actually 2, roughly 2. This is called the g factor of the electron. It's roughly 2. And this is a huge puzzle because this leaves completely open the question that what does this spin actually mean and how do we incorporate it into our Hamiltonian and into our Schrodinger equation. And many people, notably Pauli, took a very practical view. He wrote a very nice paper, which I have here with me. I just started reading it yesterday again, on the quantum mechanics of magnetic electrons. And basically, it meant what is the quantum mechanics of the dipole moment of an electron. And in that, he simply proposed that the Hamiltonian of the Schrodinger equation be generalized in such a way that you have Schrodinger's usual terms like this, multiplied by, let's say, a 2 by 2 matrix 1, plus a term, or actually minus mu E dot B. So the Hamiltonian gets modified in an external magnetic field. This is the external field. And this one we should just fix by experiment. So experiment says that it's roughly equal to 1 Bohr magneton, not half Bohr magneton, but okay, we just put it by hand. And by the way, you probably know this is the paper where the famous Pauli matrices were introduced. Okay, because once we look at objects which have a angular momentum of half h bar, they are actually described by the representation of the rotation group is in terms of those matrices. Okay. But why should G be equal to 2 was an unsolvable question, and Pauli was not able to address that. And this is where we come to Dirac. And this is where things started to get more interesting, and also to change in a way that completely changed what quantum mechanics means, or largely changed. Okay. We can still use all the things I've told you for certain systems, but we can't use them for most general systems. So Schrodinger equation is certainly wrong for general systems. So let me again pause for questions.
Hello, good morning.
Yeah. Good morning.
Yeah, am I audible, sir?
Yes, yes.
Sir, thank you for revising all this basic concept of quantum mechanics, sir. I just have one question. Like, sir, you have discussed about the matter waves. So I have the question: does the dispersion of matter waves have any effect on the computing in controlling the qubits and its manipulation, sir?
Probably, I would think so, because I think it's an important property of the. I don't know in detail how it would affect the control, but basically dispersion simply says that frequency and inverse wavelength are not the same thing as they are in light, but there's a maybe quadratic, maybe square root, maybe some other relation between them.
Yeah.
Okay. Even saying energy is p squared by 2m is a dispersion relation. It's not true for photons, where energy is actually equal to p rather than p squared. Linear dispersion relation. And in graphene
Yeah.
also there's a linear dispersion relation. So yeah,
Yes.
how it concrete. So you could ask this question in the next few days to the people when they talk about actual
Sure.
quantum computing. But it's a good
Yes.
question, because obviously this is an important characteristic of the matter wave.
Thank
And
you.
so it will
Thank you.
vary from one type of matter wave to another.
Right, sir. Thank you.
Okay.
Can I add something, sir?
Please.
I am Professor Panigrai. Actually, this question arises and because of the matter wave, de Broglie wave, and there is a wave function associated with it, and because the Schrodinger equation is linear.
Yes. Hello. Hello.
And that is the
Yeah.
basic ingredient of quantum computation.
Yeah. Sorry, I lost you for a few seconds. Can you just repeat the question? I don't know if it is me or him, but I'm not hearing anything. Are other people there?
Yes, sir. We are here, sir. I think there's
Okay.
some network
I
issue.
think I see he has a network issue, perhaps.
Sir, can you extract a energy time uncertainty relations from wave mechanics?
Yeah, so thank you. That's a much more complicated question, and it doesn't have the same status as the position and momentum uncertainty. But you see, it has a different meaning, because energy and time are actually not operators in the same sense. Time is not an operator in non-relativistic quantum physics. Only x is an operator and p. So you have to talk more in terms of measurement. We do use the relation. We do use the. You're asking whether I can derive it from old wave mechanics. Yeah, probably. I think it's probably the same thing. But you need to talk in terms of the time during which you are measuring the frequency of a wave. So you see, energy basically is frequency. So energy time in quantum physics comes from frequency time in classical physics. So just like wave number was conjugate to position, it is the frequency which is conjugate to the time. That together they obey the relation. And that relation basically, I think, comes from the fact that in order to resolve the frequency of a wave, you need to measure for a certain amount of time, right? And you can see why. Because how will I know the frequency? I'll know it by waiting for two crests of the wave to pass me. And then I'll say, aha, the distance between the crests gives me the wavelength. From that, I know the frequency. Okay. But I can't do that if I don't have enough time for both the crests to come and pass me. So I need a finite amount of time, maybe very small, that doesn't matter. But if I want to resolve the frequency very accurately, then in fact, if the frequency, particularly if the frequency I want to resolve to very fine accuracy, then I'll need to look at many crests passing me, and I'll need more and more time to get that accuracy. So it's really a question of accuracy of measurement. So it's a little different, it's little but importantly different conceptually from the delta x, delta p. And what you'll see in my lecture this evening is that T is not an operator in quantum mechanics. But in quantum field theory, even X is not an operator. We simply get rid of X and T as operators and we make them all parameters. And that is a key step which makes, which defines quantum field theory. The operators are the fields themselves. So instead of the wave function being the state and the position being an operator, we find that the wave function is replaced by a field and the position just becomes a parameter on which the field depends. But I'll do all that later.
So that means that there is no kind of uncertainty in quantum field theory. That's what you mean.
No, there is uncertainty, but now it is between fields.
Okay.
There is still uncertainty, but it's a little more abstract. You might think that it becomes like, just to give you a rough analog, in electromagnetism, when we quantize it, we have an uncertainty roughly between the vector potential and the electric field, something like that. So there is an uncertainty in quantum field theory, but it doesn't apply to the positions. The point is that these are not positions of particles anymore. We simply drop the particle description. Let me come to that in the afternoon. So now I don't know, Dr. Panigrahi vanished and I don't know if he's back. Are you back, sir?
Yeah. I am here, sir. I am here.
Your question disappeared in the middle. So if you want, you can ask it now.
Okay, no problem. No problem.
No, go ahead. You were asking some question, right?
No, I'm just supplementing the question asked by.
So tell us what you said because I didn't hear it.
Yeah. Thank you.
Okay, maybe we can bring it back later. All right. So now we come to Dirac. And with Dirac, something really different and new happens. And it highlights a new way of thinking about physics, which again is forced on us. And the reason has to do with, actually a lot has to do with Dirac's own way of thinking. So I'm going to open the paper in front of me. Atri, you should tell me when you want me to stop, huh?
Okay. Actually, officially it's like 12, but we have started late.
Yeah.
So we can continue up to 12:15, 20,
Yeah, we started at 11, but yeah. I'll wind up in about 10 minutes and then we can have questions.
Okay, as you wish.
Yeah, okay. So Dirac's paper from 1928 says the new quantum mechanics, when applied to the structure of atoms with point charge electrons, does not give results in agreement with experiments. And he's referring to the fact that there are two states where we would expect one state. This is what I told you. It was the splitting which showed us the states, but even without splitting, there are two states of an electron, but there's only one particle. And Dirac writes, to meet the difficulty, Gaudsmit and Uhlenbeck have introduced the idea of a spin angular momentum of half a quantum and a magnetic moment of one Bohr magneton. And then he says this model has been fitted into quantum mechanics by Pauli and Darwin. Okay. And it works. But he says, why is nature choosing this peculiar thing to throw in a spin into the problem? And could it be that we have not properly understood what he calls duplexity phenomenon? Duplexity is the doubling of states due to spin. Now, what I find striking about this introduction, this is the doubling or splitting of states. What I find remarkable is that nobody else was asking to explain the phenomenon. They said, look, Pauli has a model works. What is your problem? I mean, model works, it's giving right answers. So what we should be doing, I think most people were thinking like that, just keep doing more experiments and then use that model of Pauli and see if you can find agreement with the experiment. Why are you asking to explain this duplicity phenomenon? He wanted to explain. And this marked the start of, if you like, an aesthetic movement in physics that, things should feel natural, things should fall, even though quantum mechanics is weird and bizarre, it should not be artificial that we have to keep assuming new things every day. And actually here you can just think in many branches of physics, we often just write down a Hamiltonian, let's say for a material, and then next person will write down another Hamiltonian for another material. But there's no rule which tells you what is the right Hamiltonian to study for a given material. Here, on the other hand, what we are saying is that there should be some kind of underlying rule. And Dirac correctly realized that somehow relativity should be giving the rule, because look, both Schrodinger equation as well as Pauli's modification with the magnetic moment is still non-relativistic, and we know that non-relativistic physics is not complete, is not true. That is what relativity is saying. It may be approximately true, but it's not exact truth about real matter. So he said, I'm going to ask from first principles, what should we be doing? So from first principles, derive. Again, you can't derive. Derive again means guess, but here it's a slightly different way of guessing. It is guessing using relativity, a relativistic wave equation. And what is relativistic? Well, the relativistic idea starts from E equals square root of P squared C squared plus M squared C for M is the rest mass. Okay, so we should have a wave equation which, instead of saying E is P squared by 2M for a free particle, we should have this rather than this. And as we all know, if you take the upper equation and expand it for small p, you'll find this as a correction term, and then there are higher order terms. And then the leading term is this one, which gives me the rest mass, E equals mc squared. So this is actually equal to mc squared plus p squared by 2m plus higher order terms. So we should use this equation itself as the basis for Schrodinger equation. So for a relativistic Schrodinger equation, so you can guess minus IH bar dE by dt equals square root of minus, this is a guess, sorry, I didn't mean dE by d psi by dt. Okay, because E got replaced by this d psi by dt, and right side we had this expression. So this is a guess for a wave equation. This is the most naive guess. Okay, now there are two problems here. One is square root has both signs. And to Dirac's credit, he didn't try to just bluff and say we are going to keep the plus sign. He realized that these two signs is a very meaningful thing. Okay, but all right, you could say that this is the equation with the plus sign and we'll only keep the plus sign. But the problem is, the bigger problem is that it's highly non-local. Because if psi is a function of x, then gradient of that is a local function. That means it depends only on behavior of psi near some that region, that point x. Even gradient squared or gradient cubed or even 10th derivative, they are all local. But this square root, if I try to expand out, then I find infinitely many powers of gradient, and that makes it non-local. So trying to expand this, we'll get the right-hand side will be del squared psi plus del 4th psi plus del 6th psi, all with some number in front, plus up to infinity. And if we take arbitrarily high derivatives of a function, infinite derivatives, then we can transport that function to any other point. You may know this. So this is definitely very bad. Okay. So next guess, this guess failed. I want to also point out that, when I say we should guess, we should also check it, and when it fails, we should realize it fails, but we should not go home and cry. We should sit there and say, if it fails, what is my next guess? This is actually the root of how science is done. You make a guess, it fails, you make another guess, it fails. You keep improving your guess using your intuition, your knowledge, and hard work. And so the next guess is quite simple, which is to square both sides. So we have minus h bar squared over d2 by dt squared on psi is equal to minus h bar squared. Sorry, I wrote something wrong. I wish somebody had stopped me. This was wrong. I did not want to write this thing at all. I was trying to write the relativistic one. I'm really sorry. Sometimes I get very absent-minded. It is minus h bar squared grad squared with a c squared plus m squared c4. This square root. We're just trying to copy this relation the way Schrodinger copied the E and P relation. We're trying to copy the same thing, but for the relativistic relation instead of the non-relativistic relation. And we are still making the substitution that P is minus I h bar gradient. And this is what we get. I'm really sorry. Please do interrupt me if I'm writing nonsense. Otherwise, we'll go away believing nonsense. Okay. So, as I said, this requires the choice of sign. So we can say plus, but it's highly non-local. That is still true. And so the next guess is that we square both sides. And now we have this. There's always c squared in it. And plus m squared c fourth psi. And this equation looks better because it is local. And it has a name. It's called the Klein-Gordon equation. It's obtained in the same, if you like, Klein-Gordon equation is a very natural generalization of Schrodinger equation by first trying to use the relativistic relation in square root form and then saying, no, we'll square both sides to get a local equation, and then we get what we get, and it's the Klein-Gordon equation. And it's a very good equation, but it has now a new problem. Now the square root becomes a problem because now this determines E squared. It doesn't determine the energy of a state because the left side of this equation is the square of the energy. So if we solve this equation and find out the energy of some system, we'll be able to find out E squared. But once we know E squared, the value of E can be plus or minus of the same thing. Okay, plus now there's no invariant distinction. Now we can't say, if we only know E squared, we cannot say that E is plus or minus with E. In fact, both are possible. And so Klein-Gordon equation has negative energy states. And this is pretty bad. But Dirac didn't like it for a different reason. He didn't want to do this squaring. He said there should be an equation which is first order in time. He doesn't care what it is in space, but it should be first order in d by dt. And he struggled, he just simply did whatever algebra it takes to find out such an equation. And he realized very quickly that if we want this, and it should imply the Klein-Gordon equation, but not be implied by it. So if it implies the Klein-Gordon equation and it's first order, okay, if you square the new equation you are looking for, it would be Klein-Gordon equation. But his view was that he's looking for a natural choice of an equation which is first order in d by dt. Now, one reason he didn't like Klein-Gordon equation is that it doesn't solve that duplexity problem, because this equation can be applied to a single wave function. So there's not a natural pair of wave functions. What Dirac managed to find was a equation first order in d by dt whose solutions are a doublet of functions, and he associated those with the duplexity of the electron. So actually for him, he said, let me assume that I have beta del by del t plus alpha 1 del by del x plus alpha 2 del by del y plus alpha 3 del by del z on psi equals 0. This is what he wanted. And then he imposed on this the requirement that squaring should give the Klein-Gordon equation. And he found that it's not possible as long as beta, alpha 1, alpha 2, and alpha 3 are pure numbers. You simply can't take this equation and square it and recover Klein-Gordon equation. In a way, you can see what goes wrong. If I square it, I'll get cross terms like alpha 1, alpha 2 times del by del x, del by del y. Okay, but those terms are not there in the Klein-Gordon equation. It has only del by del x squared and del by del y squared and del by del z squared, but not any cross term. So then he realized that can only be done if alpha I and beta are matrices. And he then set about constructing the matrices. But if these are matrices, then psi must be a multi-component wave function. And he realized right away that this can accommodate spin. Hopefully, if psi has only two components, like in Pauli's theory, then these two components can be the spin up and spin down wave function of the electron. But unfortunately, and Dirac was very rigorous in mathematics, he was a mathematician actually, he found that actually there are four components, and the other two caused a lot of puzzle, and one of the puzzles was that again negative energies come in. So these were good, and these other two components had negative energies. So this awful problem of negative energies was not going away. And this is a good point for me to stop for the morning talk, because the entire evening session will be devoted to the question, what do we do with these negative energies? I just want to emphasize before I completely stop that ultimately there is a square root, and it is that square root of it is the relativistic expression which is to blame. So you should blame Einstein for this negative energy problem, because E is equal to this. In classical physics, you can say E is just taken to be the positive root, but in quantum physics, you can't, because if we don't take even if we take the positive root, the negative root is a available state of the system, and the positive energy particle can go and fall into that negative energy state, and that will destroy everything. So that's where I'll stop. Hello?
Yes, sir.
Yeah. Okay.
Okay.
So I'm stopped, so I can take questions.
Yes, sir. So once again, thank you, sir, for a truly thought-provoking and engaging session, and for revisiting the foundational principles of quantum mechanics with such clarity. It has truly been a privilege to benefit from your deep expertise